let's do one more example. So again, this is another example of G acting on itself. This is also an extremely important example of a group acting on itself. So what is this? So this is called conjugation, action by conjugation. So given G in G and S in G, define G star S. I'm going to use star here to be very clear about the action. This is star refers to the action, not the product inside the group. Earlier I could be slightly vague because action is already the product inside the group. Here I define it to be G star S is GS G inverse. So GS G inverse is called conjugation of S by G. Okay, so this is called the conjugation of S by G. This is conjugate of S by G. So I should not write conjugation, it's called conjugate. The process of doing this is called conjugation. So is this an operation? Is this an action? Let's check this. Is this an action? So you have E dot or E star S. What is E star S? It is by definition, so the action is defined to be this. E S E inverse, which is E S E, which is S. So that's okay. What about G1 G2 star S? By definition this is same as G1 G2 times S times G1 G2 inverse, right? This is the action. But this is same as G1 G2 S G2 inverse G1 inverse, right? Because that is inverse in a group. Product of G1 G2 inverse is G2 inverse times G1 inverse. This is G1 G2 S G2 inverse by associativity of group operation, and this is G1 G2 star S G1 inverse, right? Because G2 star S is by definition G2S G2 inverse, but this is same as G1 star G2 star S, because G1 star something is G1 times that thing times G1 inverse, right? This is the operation. So G1 star, this middle thing, G1 times the middle thing times G1 inverse is G1 star that middle thing, right? So this says that G1 G2 star S is G1 star G2S. So star is an operation, is an action. Again, what I am doing is not a formality, okay? It is, there is some content in this. Star is an action, the identity is okay, that is very clear, but the associativity required a small proof, right? So this is called, this action of G on itself is called the conjugation action. Okay, so the two actions that we have studied by G on itself are the left multiplication and conjugation, and both are extremely important. Okay, both are important because of the results that we can prove using these actions later. Okay, so this is the, for now let me stop with examples here. There are some other examples that I will come back to later, but now let us see some properties of group action. So now let us continue with our study of, as I said, this is actually an easy notion, group actions. Initially, if you are saying it for the first time, it is somewhat strange, so it will take some time to get used to. That is the only difficulty. The unfamiliarity is the difficulty. So please understand the examples very carefully. So I have given 5 examples. First one being how rotations operate on the vertices of equilateral triangle. Then our familiar symmetric group acting on the indices. Invertible matrices acting on column vectors. And finally, the 4th and 5th examples were a group acting on itself first by left multiplication and then by conjugation. So these are the important examples, and if you understand all the examples carefully, it also illustrates the point I made earlier, that group action is supposed to be abstract. It is not in some specific context. In any context where you have a group and a set S and a function from G cross S to S satisfying some conditions, we have a group action. So now there are some obvious, some important things that we can attach to group actions, and they are the following. So let G, so the general situation is, let G be a group acting on a set S. So G is an abstract arbitrary group, S is an abstract arbitrary set. Let small s be in capital S. The orbit of S, of small s, denoted by OS, orbit, O for orbit, S is, OS is all, so you take GS. Okay, so see the word orbit, you know the word orbit, it's how an object moves around, right? It's the orbit of the earth around the sun, for example. It's how earth moves around the sun, you connect all the points where it travels and you get the orbit. The same idea works here. You take a small s, orbit is always defined to be, orbit is always defined for a element of the set S, and see where it travels under the action of G. So you take one group element and see what is GS. So I am going to use GS to denote the action. So here we have G cross S to S. I will take a small g small s and I will denote its image by GS. I will not use star or dot just for simplicity. So I take small s, see wherever it travels under the action of capital G. So small g, take one element small g, take another element G prime, take G double prime. You do this for every element of small g and see where it travels, and you see, call that orbit of S. Orbit of S is of course a subset of capital S. So orbit of S should be thought of as the set where small s travels under the action of G. So you see where small s travels under the action of G. Okay, now I should quickly check in all the examples orbits. For example, okay, so under the first example, G was the group of rotations and S was the vertices. What is the orbit of S, of let's say of A? Now if you go back and see the orbit action, A will always be in the orbit because identity A will be A, and R1A was B, R2A was C. So orbit of A in this case happens to be S, right? Similarly, this is also orbit of B and orbit of C. In the second one, G was the symmetric group and S was the indices 1 through n. What is the orbit of 1? 1 is there, certainly, because identity 1 is 1. 2 is there because 1 2 sends 1 to 2. 3 is also there because 1 2 applied to 1 is 2, 1 3 applied to 1 is 3, 1 I in general is applied to 1 is I, right. So in this case also orbit of 1 is all of S, and as you can see this is orbit of 2, orbit of 3, orbit of N. So they are all S. In the third example we have G is GLNR and S is Rn. If you take the 0 vector, okay, in the previous 2 examples you might think that orbit is always equal to the all of set, but that's not necessarily the case. So what is the orbit of? If you take any matrix A and multiply by 0, you get 0, right? So orbit of 0 is just the element 0, nothing else is there. And now on the other hand, if you take a vector, this is an exercise that you can do using properties of matrix multiplication. If V is in Rn and V is different from 0, then the orbit of V is all of Rn minus 0. So this is to say that, in other words, given any non-zero vectors V bar and W in so I don't need a bar here, so W in Rn, there exists an invertible n by n matrix A such that A dot V is W. So what I am saying is that let's take this as a fact, okay. This fact can be independently proved. That's not part of the what I am now talking about, so I don't want to spend time on this. But what does this fact mean for the orbit of a vector V is what I am interested in. Suppose this statement is true. Given any two non-zero vectors V and W, there exists an invertible matrix A such that A dot V is W. Then this implies that orbit of V, remember in order to get this W has to be non-zero also, is all non-zero vectors in Rn. In other words, it is Rn minus the element 0. Okay, because if you recall what is the orbit of V, by definition it is A dot V, as A varies inside the group, in which case, in this case GLN. So you take A dot V as A varies, but because of the fact you give me any W in Rn minus 0, there is an A such that AV is equal to W. So every W will be in the orbit. So in this case there are two orbits. 0 vector is an orbit by itself and all non-zero vectors are orbits by itself, one orbit together. So now G acts on G by left multiplication. Right? In this case what happens? So take an element S in G. What is the orbit of S? Let's calculate this. Orbit of S is GS, as because GS is just, in this case action is by left multiplication. So when I write GS, I mean actually the multiplication in the group. It is GS as G varies over capital G. We claim that orbit of S, so again it's small s, okay, is all of G. Why? So the proof of this. So a priori it is a subset of G, right? It's a subset of S. which is of course G. Orbit is a subset of capital S. In our example, it is capital G. Why is orbit of S equal to G? So take any T in G. Okay, let T be any element of G. Can we find a group element G such that GS is T? See, again let me remind you, orbit is the subset of capital S through which smallest travels under the action of G. So S is fixed. Whenever we talk about orbit, the small s, which is an element of capital S, is fixed, and you are applying all group elements to it, and what you get is the orbit. So now in order to prove that OS equal to G, take any element of capital G and you want to, and which I am calling small t, we want to find a group element such that GS equal to T. Of course we can find such an element. What is G? G is simply T S inverse, right? If you take that, because here G is playing two avatars here, remember, G is the group as well as the set. If you do TS inverse times S, what do you get? This is TS inverse S, which is T. So every element, so this means that every T is in the orbit. So OS is G. So again the orbit is all of G. And finally let's look at the last example. G acts on itself by conjugation. And this is more interesting. Okay, here the action, remember, is G star S. I am going to now use star because here it's not multiplication of the group. GS G inverse, right? So recall. Now let's look at the orbit. For example, orbit of E, OE is, I take arbitrary elements of G and apply star to E. This is by definition of the action GE G inverse, as G is in G. But GE G inverse is E for all G. So GE G inverse is E for all G in G. So this is just E. So orbit of E is E. Now let's go back to the previous example. I said orbit of every element is equal to G, and in fact I should probably spend a minute more on this just to illustrate this. What is orbit of E in this example? It is GE as G where is in G. This is just G in, okay. So I have proved that orbit of every element is G. So this checks out here, right? Orbit of E is G. In particular, orbit of E is G. But whereas conjugation behaves very differently. Orbit of E is E. So orbit of E is just E. Okay. Now suppose for a moment that G is abelian. Then what is the orbit of, let's take an arbitrary element S in G. Then OS is by definition G star S, G in capital G. This is by definition GS G inverse, G in G. I have now assumed that G is abelian. If G is abelian, this is same as S G G inverse, G in G. But then SG G inverse is S, right? This is true for all G in G. So this is just S. So orbit of S. So if the group G is abelian, or orbit of an element is just that element. So these are the 5 examples. In the 5th example, we get something interesting if the group is abelian. So now coming back to orbits. Hopefully it is clear by these examples. If G is a group, an arbitrary group acting on a set S, if you take a small s in capital S, small s always contains S, right?
Sir, how much time it will take, sir?
2 minutes.
Okay.
Small s always contains S, right? So orbits are never empty. And they always contain the elements. Why is this? Because remember, OS is GS as G varies. So in particular can take G in G to be E. So ES, which is S, belongs to OS always. Okay, so orbits contain small s, but they could be just a small s or they could be all of S. So in this example of an abelian group and action by conjugation, the orbit of an element is just that element, nothing else. Whereas in the action by left multiplication, orbit is all of the group, all of the set. In the action of GLNR on Rn, orbit of the zero vector is just the zero vector, but orbit of any other non-zero vector is the set of all non-zero vectors. And in these two actions, the action of rotations on the three vertices or action of Sn on the indices 1 to n, orbits are the entire sets. So orbits are at least going to contain small s. Orbit of small s contains at least small s, and it can vary in size depending on the action. So we have seen examples of different kinds of orbits. So in the next videos we will study further about orbits and other important properties of actions, and using these properties we will prove our main theorems in the rest of the course. Thank you.